Question 2. It asks us to, in part A, to calculate the magnitude of the electrostatic force acting between two charged spherical water drops with the given charges, identical charges and given separation, and then B, how many excess electrons on each drop, giving it that charge. Now, first things first, why the term electrostatic? Why not just electric or electrical? Would have made no difference if we said electric or electrical there to answer this question. Electrostatic just means we're considering this to be a static situation. In the following sense. For the kind of situations and questions that we look at, you have a bunch of charges, you have got electric fields, the charges in the electric fields feel forces just by being present in those electric fields. And electrostatic just highlights the assumption that whatever is responsible for the electric fields in the situation we're looking at, those charges are assumed stationary. This distinction is made because the situation becomes more complicated if you're trying to bring into account movement. So in this question, it just means that we're considering these two charges, these two spherical water drops, to be stationary, just for the purposes of calculating what forces between them due to the charges that they have. So this is just Coulomb's law that we're using. It's just electrical force that we are calculating. So nothing strange. Just get used to seeing this sometime. You might see this term used here and there. Later in the course, we'll look at more deeply into what happens when things start moving a bit more. Okay, so for 2a, this is just the electric force. So K times absolute value of the charge on the one times absolute value of the charge on the other over the radius between them, the distance between them squared. Okay, now which value for K am I going to use? Well, sometimes we use this one and sometimes we use this one. Which one to use? In this example, it won't really make a big difference. How am I going to reason about this? Well, what accuracy do I have? If I have a lot of accuracy in terms of the values given by the question, then I'd rather use this more accurate value for K. If I have much less accuracy, then I'd rather use this. So what kind of accuracy do I have? I have the charge and the distance between them given to an accuracy represented by 3 significant figures. So both the charge and the distance between them, the question is confident enough in giving it to us, both of them, to 3 significant figures. So I'd rather use 3 or more significant figures for the other values if possible. So I'd rather use this one. But I mean, it's just comparing 3 significant figures to 2 or to 4. So given that this whole thought process is just a rule of thumb to keep track of how uncertain our calculations are, it would have been fine to use either one. Don't expect to be penalized if you use this one instead. Talk a little bit more about that at the end. So what is the charge? It's absolute value of the charge on the one. That's plus 1.00 times 10 to the minus 16 it was. Coulomb's other one's the same, so it is squared over the distance between them squared. It's 1 centimeter. And notice I write it as 1.00 still, so I can easily read off the significant figures of everything. And let's calculate this. I like to do questions like these, separate these powers of 10, calculate it afterwards separately. So I first take this times this times this. So it is 8.988 times 1 divided by 1 divided by 1. So it's just 8.988. And now times 10 to the what? Okay, so I've got a 9 there. I've got 2 minus 16s there. And I am dividing by what? Okay, what 10 to the minus or plus what am I dividing by? I've got 10 to the minus 2 here. It gets squared, making it 10 to the minus 4. So I'm dividing by 10 to the minus 4. So that is plus 4. This is 10 to the minus 19. What's newtons. Okay, now this is a final answer. I'm not going to do anything more of this with this value, so I'm going to give it to a sensible number of significant figures. How many? I'm just multiplying, dividing, so I'm looking at the least number of significant figures, which are these two, which are 3. Both have 3. So I'm just going to provide 3. And there we go. Oh, this pen is... Okay, over to black. Okay, and that is A. Now for B. This is just the number of excess electrons. Okay, so my charge is on each drop is minus 1.00 times 10 to the minus 16. So it's a negative charge. That means there are more electrons than protons. So suppose there are n more electrons. So in other words, n excess electrons. Then what would the charge be? Well, if there are n excess electrons, then the charge would be n times, and here again I rather use the more significant figure version of the charge of an electron. I'd rather use minus 1.602 times 10 to the minus 19 coulombs instead of just 1.6, because the other value in the calculation has 3 significant figures, not just 2, and this should be minus 1.8, like that. Okay, so what's the reasoning used here? I mean, it's simple. Suppose you have a bag and with a bunch of marbles, and the bag weighs 360 grams. That is its mass. We don't know how many marbles are in here. We know that each marble weighs 20 grams, and the whole thing weighs 360 grams if excluding the mass of the bag itself. Then how many marbles are in here? Well, 360 divided by 20 equal 18. Okay, so then there are 18 marbles in here. Okay, so that is mathematically the logic we're using here. It's the exact same situation mathematically. Not the exact same situation physically. I mean, you don't have marbles cancelling one another out like you have negative and positive charges cancelling each other out. But just in terms of finding the number of marbles here and find the number of electrons here, mathematics is the same thing. Total divided by how much each one is. So 8 is just this divided by that, and that is 1 divided by 1.602, and so 10 to the minus 16 divided by 10 to the minus 19 is going to be 10 to the 3, so that 10 times 10 to the 3 would then be 624.2, or approximately 623. Why do I write 3 there? Approximately 624. Okay, and that's your answer. Now, some of you might have got 625 if you just used 1.6 times 10 to the minus 19 here. That is okay, that is still acceptable, don't worry about that. In terms of which value to use this one or to use that one, or to use 1.6 or to use 1.602, which one makes more sense? In this situation, it's comparing 3 significant figures to 2 or to 4. I mean, it is not that big of a deal, especially since it's just a rough rule, just a rule of thumb to keep track of the uncertainty of the values in our calculations. If the charge is given more accurately, let's say, for example, the charge was given not as that, but instead as minus 1.2378 coulombs times 10 to the minus 16 coulombs. Let's say the charge was given as that instead. Then, if you were to then calculate the number of excess electrons by taking this and dividing it by, so doing the same thing here, but all it did was to divide by this, then that would be a bit more of a penalizable error in judgment. You have a very accurate value here. How accurate? Well, accurate to 5 significant figures. Yet you divide by something only accurate to 2 significant figures. So you have a very accurate thing, but you kind of spoil that accuracy by using another value in the calculation, which is far less accurate. So in this case, it would make more sense to use the more significant figures for this one, or you can go and look up the actual charge, or the more accurate, the the charge of electron with even more digits. I mean, there's more here. This is still not the exact charge, so you can go and look up even more digits for the electron charge. But the point is, I mean, the two you'll see used a lot is just 1.6 and 1.602. The point is that if the charge was given like this, 5 significant figures, and it would have made more sense to use this instead of that. And instead use a more accurate value to match the accuracy of the other value in the calculation. So in a more extreme case like this, it becomes a bigger issue whether you want to use just minus 1.6 times 10 to the minus 19 or minus 1.602 times 10 to the minus 19. But in this case, it is not a big deal. Even this answer is not, it's a very rough answer. I mean, this value here, this charge, this is, I have to assume that this is some sort of measured value, or person who gave this values is only confident in giving it to 3 significant figures. So, I mean, a fair assumption would be that the actual charge in a given situation would be anything from minus 0.99 times 10 to the minus 16 to minus 1.01 times 10 to the minus 16 coulombs. Now, if you take that into account and calculate the number of electrons that way, it means the answer can be anything from something like 615 to 630 if you were to calculate it. So this is a very rough answer, so it's absolutely no problem if you got 625 or anything. Or 627 or whatever. This is a very rough answer, so don't worry too much about something like that if your answer is out by that last digit is not the same. Okay,